I'm going to present experimental data on angular resolve photo emission data on a single layer strontium glufosinate. We worked on this material for many years. It was actually the project of our first PhD student in the group. But things actually start working and becoming interesting when we got high resolution data from our home lab. And at the same time, we start collaborating with the group of Antoine Georges, in particular with Manuel Zing. The sample that we measure were grown by Alex Gibbs during her PhD at the time at University of St. Andrews in the group of Andy McKenzie. So the interest on strontium-2 ruthenium-04 is twofold. On one end is a superconductor, an unconventional superconductor at very low temperature, and people are still trying to understand what is the symmetry of the order parameter. In the normal state is a Fermi liquid and an exceptionally clean Fermi liquid. So it has a mean free path that is equivalent to 1,000 lattice spacing. What you see is the in-plane resistivity measured over a very large temperature range. And it's a good Fermi liquid below 25 Kelvin with a T-square resistivity. But as you increase temperature, you see that the temperature dependence is not T-square anymore. The resistivity doesn't saturate and it becomes a bad metal. I think you will hear more in the next talks this morning about this Fermi liquid to non-Fermi liquid transition. I will focus on the Fermi liquid phase at low temperature. So I'm going to introduce the key ingredient in this system. It's a multi-orbital material where there are 4 electrons in the ruthenium-4d shell that occupy the T2G orbital, so the in-plane dxy and the out-of-plane dyz and dxz. This Fermi liquid is dominated by a very broad range of energy scales. That's what you see in the diagram here. But unlike normal, or unlike MOT insulator, where the correlation comes from the vicinity to the MOT insulating phase, and the properties are dominated by the Coulomb repulsion U and the bandwidth. In this system, it was highlighted from theory that the strong correlation come from the Hund's coupling J. And for this reason, this is called the Hund's metal. It belongs to a large family of material, and it's the topic of this morning's session. I will show you in my talk that there is another important ingredient, which is the spin-orbit coupling. And what we find from combining experiment and theory is that spin-orbit coupling is actually much larger than what you would expect from a simple band structure calculation. So I guess most of you are familiar with the Arpes Fermi surface of strontium-2 ruthenium-04. This was measured by Andrea Damascelli basically 20 years ago. It consists of a large round Fermi surface contour called gamma, and 2 square-like Fermi surface called beta and alpha. And zero approximation, the gamma band has mostly dxy character, and the beta and alpha band has mostly dxy dyz character. So now I will show you state-of-the-art data on the same material. This is the Fermi surface measured by us using a laser as excitation source. We are able to measure the Fermi surface with much higher accuracy than what was done before. And I will discuss 2 aspects of this Fermi surface, spin-orbit coupling and how electron correlation manifest themselves as you move around these Fermi surface contours. Getting such data on strontium-2 ruthenium-04 is not easy because there is a fundamental problem. When you cleave a sample in UHV, there is a reconstruction of the top layer. The ruthenium oxygen octahedra rotate and form a square root of 2 times square root of 2 superstructure. So in general, a clean sample will show a lot of bands at the Fermi level, which is what you see here on the right-hand side, which are bulk states, but also surface states. And these bands are backfolded due to the additional periodicity. So many ARPES group tried to find a recipe to quench the surface state. What we did was to follow surface reactivity studies done by the Diebold group in Vienna, and figure out a particular recipe to quench the surface state. So what we do, we expose the sample to a control amount of carbon monoxide at a high temperature. And then when we cool down the sample, we see that the surface state are completely quenched. This is quite clear if you look at the dispersion plot along the gamma M direction. A clean sample, a freshly cleaved sample shows surface and bulk states. After this CO exposure, all the surface bands are quenched and you are left with a clean image of the bulk electronic structure. I stress this because this surface problem caused quite some confusion in a surface sensitive spectroscopy study of strontium-2 ruthenium-4. This confusion, it's never very clear when you measure the system, whether you're looking at surface state or at bulk states. An example is a recent STM work, which was done by the Madhavan and Davis collaboration. They measured these samples and they address what are the strengths of electron correlation, what is the symmetry of the order parameter, and actually their data fits very well with the ARPES data, but what they actually see, and that's what these are the green dots, so it's the dispersion derived by the quasi-particle interference data, fits exactly the surface states and not the bulk electronic structure, so it's a delicate issue. So the experiment that I'm showing you were done in our home lab, where we combine a 6-axis goniometer that allows us to cool down the sample below 4 Kelvin. As excitation source, we use an 11 eV laser, and you operate an MBS electron spectrometer with some millivolt electron resolution. So I say a few words about this laser because it's a bit the key instrument. It's a relatively new and delicate system. So to produce 11 eV, you start with an infrared pulse laser. You mix this together with a force harmonic into a xenon cell, and you produce the 9 harmonic of your infrared laser, which correspond to roughly 11 EV. Producing a high harmonic light with a picosecond laser is actually quite difficult. It's much easier if you use a femtosecond laser because the peak power is higher. So you need a very high conversion efficiency in your system to produce enough photons to run your experiment. Okay, so let's discuss the data. The first thing I'm going to address is spin-orbit coupling. It is known spin-orbit coupling is an important effect at the Fermi surface. It opens a gap at points where bands would be degenerate. It produces a mixing of the orbital content, and it produces a finite orbital angular momentum. At the DFT LDA level, the spin-orbit coupling strength is 100 millielectron volt. There are some experiments that try to quantify the spin-orbit splitting. This was done by the group of Andrea Mascelli, combining spin-resolved ARPES and circular dichroism. And what they did, they look at the splitting between the alpha and the beta band, a few half an EV below the Fermi level. And I would say accidentally they found a value that is not too far from what LDA expects. However, there is, until recently, there was not much discussion of what happens of spin-orbit coupling in the presence of electronic correlation. There was some theory work, there is some early work from the Anderson group. They try to understand the ARPES Fermi surface of strontium-2 rhodium-4. These are these light gray contours that you see in this plot, and they figure out that in order to reproduce this Fermi surface, you need to take into account correlations and spin-orbit coupling, and they prove by they prove that spin-orbit splitting is enhanced by Coulomb interactions. There is much more modern DMFT theory that look at this problem. Spin-orbit coupling reveals itself as a off diagonal term in the self-energy, and what the MFT finds that these off-diagonal terms are frequency independent, and the effective spin-orbit coupling is basically twice what you expect from LDA. Now, as an experimentalist, it would be nice to understand from experiment what is the strength of spin-orbit coupling in this system. And I will show you that it's, from experiments alone, this is not at all obvious. If you think you have two degenerate bands that open a gap due to spin-orbit interaction, in the presence of correlation, you will have this band will renormalized, and if what you could do in experiment, you could measure the energy splitting at a given point or the momentum splitting between these two bands. What was shown by Min-Jae Kim and Antoine Georges is that actually this splitting in energy and in momentum will depend on the quasi-particle residue Z and on the bare velocity of the bands. These are two quantities that from experiment you don't know. So from experiment alone, looking at some splitting somewhere on your band structure close to the Fermi level will not tell you what the spin-orbit coupling strength is. So what we did, we combined experiment and theory. Our approach was to look at the Fermi surface, look at the particular cut where at the DFT level you would expect the beta and the gamma band to be degenerate. In experiment, there is a large splitting, and we quantify the splitting and we compare it with the splitting that you would expect from an LDA calculation, which includes spin-orbit coupling. Then you see that the splitting in the experiment is basically twice what you would expect at the LDA level. And from this, we derived an effective spin-orbit coupling, which is 200 millielectron volt. And it's exactly what was predicted at the MFT level. If you take into account this enhancement of spin-orbit coupling due to interaction, you find that you increase the spin-orbit coupling in your calculation, you find a very, basically a perfect agreement between ARPES and the calculation. What happens is that, for instance, the beta band, upon increasing the spin-orbit coupling, gets a bit smaller, and the gamma band gets a bit larger, and therefore fitting well the experiment. You should not think at this as a change in orbital occupation of the orbital. It's a change in orbital character of the Fermi surface. So the beta band gets a bit smaller due to the influx of the XY orbital in that band. And indeed, the effect of enhancing spin-orbit coupling is to produce a very large orbital mixing everywhere at the Fermi surface. So if you have zero spin-orbit coupling, these bands have a pure dxy and dxz/yz orbital character. As you turn on spin-orbit coupling, they tend to mix primarily close to the zone diagonal, but when spin-orbit coupling is enhanced by correlation, there is significant mixing everywhere along the Fermi surface. And you will notice that there is no place at the Fermi surface when the bands have pure orbital character, which means that you have finite orbital angular momentum everywhere on the Fermi surface. I stress this because I think it's important for, if you want to understand the superconductivity, the symmetry of the order parameter, to consider this strong mixing at the Fermi surface. The second thing I want to discuss with you today is the quasi-particle dispersion, how this changes as you move along the Fermi surface. So this is what you see here as a series of dispersion cut that were measured starting from the gamma M direction to the zone diagonal, and you see the beta band and the gamma band dispersing. So if you start from the gamma M direction, you see that the beta band is significantly steeper than the gamma band. The velocity is basically 4 times the one of the gamma band. And as you move to the zone diagonal, you see that the velocity changes, and that along the zone diagonal, these two bands are basically parallel. They have the same velocity. So for the rest of the talk, I will try to explain you where this strong angular dependence comes from. before doing that, we need to check something. So we can use all these this complete set of data to extract what the cyclotron mass is. So from experiment, we can estimate the Fermi wave vector, the velocity, and if you integrate this, you can calculate the cyclotron mass, which is what is found by quantum oscillation. So you can compare these values, and then you find that finally ARPES produces cyclotron masses that are consistent with the HVA. This took quite some time. Normally ARPES group measured the Fermi velocities along the two high symmetry direction, then came up with some assumption to produce the cyclotron mass, and the number never actually fit well with quantum oscillations. If you do this complete, if you make use of this complete data set, you actually find that the two are in very good agreement, which also makes us very confident that what we see is the bulk electronic structure and not some surface states. Okay, so let's discuss about this strong angular dependence that we see. We just, well, one thing is to look at the velocities. The other thing is you can do is to extract the real part of the self-energy, and that's what we did. So you see here an example of a data set. We fit all our MDCs to extract the quasi-particle dispersion. These are these green and yellow dots that you see here. And then we calculate this real part of the self-energy as the difference at the given energy between the ARPES states and what you would expect from the bare Hamiltonian. This is a standard procedure which is done in many ARPES studies. The peculiarity is that as a bare Hamiltonian, we consider the DFT plus SOC band structure with enhanced spin-orbit coupling. So this enhancement of spin-orbit coupling comes from correlation, but it's a static term, so it's frequency independent, and therefore it makes sense to use it. It's important to include the SOC, the enhancement of SOC, because especially in directions where the gamma band is close to the Van Hove singularity, there the velocity would goes to zero, and you need to the real part of the self-energy you would extract would not make much sense otherwise. So I show you the result of the analysis for all the angles that we measure. You start from the gamma M direction, where the self-energy for the gamma band is significantly higher than the beta band, and as you move to the zone diagonal, they get closer and closer together, and they superimpose at the zone diagonal. You can see the same if you look at the mass enhancement, the ratio between the bare velocities and the Fermi velocities in by ARPES. As you move along the Fermi surface, you see that there is a large difference for the gamma M direction, and then they move together along the zone diagonal. So if you this is a large effect, and if you would think at it in terms of a Fermi liquid with a single band and only local interaction, you would not expect at all such a large angular dependence. And you could now discuss whether this is the signature of coupling to some spin fluctuations or electron phonons. I think that this description is actually quite misleading and prone to some misunderstanding, and it comes from the fact that we are not dealing with a single band Fermi liquid. It's a multi-orbital system, and I will show you that this large angular dependence actually changes significantly if you look at the problem instead of in the band basis, in the orbital basis. So I show you the principle of what we did in these slides. In these slides, it's not exactly how we did it. You can look at the details in the paper, but so you start from the alpha, beta, and gamma, and the x, y, dy, z, and the xz orbitals. These are complete basis, and you can go from one to the other with an unitary transformation if you know what is the orbital character of each band at given k value. This transformation is is straightforward for the Hamiltonian. Here it's also described for the self-energy. So in principle, if you know the self-energy in the band basis, you can extract the self-energy in the orbital basis. The self-energy is actually a matrix with 9 terms. Experimentally, what we can extract is the 3 diagonal element. And so this transformation makes sense as long as the off diagonal terms are smaller, but we check that, and this is the case in our situation. So I show you the result of this unitary transformation. This is shown here. So on the left side, I summarize all the data that I showed you before. The self-energy in the band basis, as you move radially along the Fermi surface, you have a very complicated situation where the self-energy changes, and it's different for every single direction. If you do this transformation, you look at the same data set in the orbital basis, you see that this separates in 2 distinct self-energy for the dxy and the dxz/yz orbital. So this large angular dependence basically disappears if you look at the problem in the orbital basis. And this is a consequence of what I told you before. There is a strong spin-orbit coupling, which produces a very strong orbital mixing along the Fermi surface. Okay, now that we obtain the self-energies in the orbital basis, we can look at the frequency dependence of these self-energies, and you see that okay, it's a bit hidden by the several windows on the side, but this self-energy has a stronger frequency dependence. It's linear only at very low frequency, and then it bends and it changes shape. Such a frequency dependence of the self-energy produces features in the spectral function that by the ARPES community are generally called kinks. So if you look at the data that I show you here, you could from a certain distance say, oh, okay, maybe the velocity changes from very close to the Fermi level, then the bands get steeper, and you could infer some characteristic energy scale. This has been done by many ARPES groups that discuss these kinks in terms of electron-phonon coupling, and many are cited here. I give you an example here. So I think that this is not the right interpretation of this frequency dependence for 2 reasons. Well, first, you can argue how clear these energy scales are in this analysis. Second thing, if you this interpretation relies on the fact that this is a Fermi, would be a linear Fermi liquid in the entire frequency range of the entire phonon bandwidth, and this is not really the case in this system, which is a Fermi liquid only below 25 Kelvin, which is a much smaller energy range than the phonon frequencies. So the reason for this strong frequency dependence becomes quite clear if you compare the real part of the self-energy extracted from our ARPES data with the MFT. The MFT finds indeed that there is a non-linear dependence of the self-energy, which comes from the frequency dependence of the electron-electron correlation. And well, on the right, there would be the DMFT shown on a much larger frequency range. There is indeed a crossover from a low frequency range that where the self-energy is linear. It then bends to it changes slope, and it turns into a second regime, and at the DMFT level, this is interpreted as a crossover from a Fermi liquid at low temperature to an incoherent state at higher temperature. Indeed, in experiment, we see no deviation from linearity for frequency above 20 millielectron volt, which is at least consistent with the crossover temperature of 25 Kelvin for the Fermi liquid to non-Fermi liquid regime. Okay, so what you see here also is that there is very good agreement between ARPES and DMFT. The agreement is good at basically at the quantitative level for the DXY orbital, a bit less for the out of plane orbital, but the essential features are there. The agreement between
Sorry to interrupt, but we're now into question time, so please try to slowly wrap up.
Okay, yes, I'm nearly done. 2 more slides. So there is very good agreement between ARPES and the MFT, not only on the orbital basis, but also if you go back to think in terms of band basis. So what you see in these graphs are the MFT spectral function. These are the colored plots, and I overplot with black, with white dots the ARPES dispersion. So there is very good agreement over the entire range of angles that we measure. And at the same time, if you look at the mass enhancement that we extract from the experiment, and what you can calculate, if you start from the mass enhancement found by the MFT, taking into account the orbital mixing, there is the MFT reproduces exactly the same angular dependence. This is kind of surprising because this is single-site MFT. It doesn't consider non-local interaction. And if you think at the physics of this material, it is known that from neutron data that spin fluctuations are actually important. So the ARPES experiment should probably capture this coupling to the spin fluctuation, and this is whereas this is not included in the DMFT calculation. Probably the signature of the spin fluctuation should be found in the small differences between the DMFT calculation and the ARPES data, or in this small angular spread that remains in the self energy. But I honestly think that these small differences are within the level of accuracy of both the experiment and the calculation. So I come now to my conclusions. I show you that correlation induces an enhancement of spin orbit coupling. I think this is important, considering this enhancement of spin orbit coupling is important if you think at superconductivity in this system. I also think mixed interpretation of the magnetic susceptibility a bit more complicated because of this orbital mixing. I show you that there is a strong momentum anisotropy of the self-energy, but this can be completely attributed to the spin orbit-driven orbital mixing. And these kind of kinks that you seem to see in the experiment are actually all related to the frequency dependence of the electron-electron correlation. What is most surprising is that the orbital seems to play still an important role in this Fermi liquid at low temperature. And yes, I wanted to show you 2 more things, but I just tell you, I think this correlation enhanced SOC is not just a characteristic of strontium-2 ruthenium-4, but is seen in other materials or members of the same family, like calcium-2, ruthenium-4, and I tend to speculate that this will also have an important effect in the bilayer system, strontium-3, ruthenium-7. And with this, I conclude, and I thank you for the attention.
All right, so I propose that online participants write their questions into the chat. Antoine, could you briefly locally answer any questions? And are there any questions in here?
Well, locally it's just Antoine and Yerni, so I don't know whether Antoine or Yerni have questions.
Then let's just go to this room over here. Are there any questions?
I have one.
Go ahead, Antoine.
Can you go back to the slide where you had the kink, the surface kink?
Yes, here, or, yeah.
Okay, so perhaps the one in which you mark the whole Fermi surface at the surface, very beginning. This green Fermi surface. Anyway, my question was, can you elaborate elaborate a little more about the surface states and the kink at the surface?
You mean here?
Yeah,
okay. Yes, so Antoine is asking about these kinks at the surface states. So well, if I go maybe once.
How did you mark the grain Fermi surface on the left?
So if you compare data from a clean sample and a sample that is then exposed to CO, you actually at the beginning you have both surface and bulk states, and then you see surface state disappear and bulk states remain, and this is kind of quite clear in the experiment. So you can do this in the cuts on this is done for the surface and the bulk state. The same I do here on the left hand side for the contours of the Fermi surface. So for the beta band, the bulk Fermi bulk contour is larger than for the surface, and then well, if you were asking about the kinks, it's kind of known that the surface bands are highly renormalized or are heavier than the bulk states. In that case, there are surface phonons that that are known to play a role.
Thank you.
All right, so thank you very much. Let's thank Anna again.